So in my last class, we understood about what is meant by photoelectric effect. So photoelectric effect was first invented or observed by J.J. Thomson when light of certain frequency falls on the surface of a metal. So electrons are ejected from the metal, and this phenomenon was known as the photoelectric effect, and the ejected electrons are called as photoelectrons, right? And we also understood what are the observations which were made after careful studies of photoelectric effect under different conditions. And later on, what is the failure of classical theory to explain photoelectric effect, and how efficiently we can explain a photoelectric effect considering quantum theory. So according to the Albert Einstein, who explained photoelectric effect by applying Planck's quantum theory, was a well justified explanation which could be given to explain photoelectric effect, right? And this is where we stopped in our previous class. And in this session, so we are supposed to understand about what is Compton effect. So Compton effect, it was first invented by Arthur Holly Compton. So it is defined as the effect that is observed when X-rays or gamma rays are scattered on a material with an increase in wavelength. So Arthur Compton, as I said, he studied this effect in the year 1922. During the study, Compton found that wavelength is not dependent on the intensity of the incident radiation, whereas it is dependent on the angle of scattering and on the wavelength of the incident beam. So this is very, very important. So what Arthur Compton he observed, and according to his concept of Compton effect, he says that so the wavelength is not dependent. Say for example, when a monochromatic X-rays are allowed to fall on carbon or some other light element, the scattered X-rays have wavelength which will be larger than the incident rays. So here the wavelength is not dependent on the intensity of incident radiation, whereas it is dependent on the angle of scattering and on the wavelength of the incident beam. Therefore, Compton scattering is due to the collision between the photon and the free electron. So he studied that so when X-ray which is having a wavelength which will be larger than the incident rays, that is the scattered rays, so which have lower energy than the incident rays. Since the scattering is caused by electrons, as I said, Compton scattering is due to the collision between the photon and the free electrons. It is evident that some interactions has taken place between the X-rays and electrons, and this has resulted in the decrease in the energy of the scattered X-rays. So Compton scattering is due to the collision between the photon and the free electron. The photon transfers a portion of its energy to the recoiling electron. So this is a diagrammatic representation of Compton effect. So here, as I said, let us imagine that this is an incident photon or a monochromatic X-ray which has been allowed to fall on the carbon. So here this is considered as a target carbon. So what happens when a monochromatic X-ray is allowed to fall on a carbon? So here the X-ray is scattered. Okay, so one will be towards this side and another will be this side and another will be towards this side. Okay, so here the scattered rays, they will have lower energy than the incident, since so when the incident radiation or photon falls upon the carbon, definitely there will be a decrease in the wavelength of the scattered radiations. So since the scattering is caused by the electrons, it is evident that some interactions has taken place between the X-ray and the electrons, and this has resulted in the decrease in the wavelength or the energy of the scattered X-rays. Okay, so here one will be the scattered photon, which will have energy of E is equals to hf dash. Okay, or it can be represented as h nu dash. Okay, another is the target electron, or this measures the mass of electron, and recoiled electron. As I said, so the photon transfers a portion of its energy to the recoiling electron. So in this way we can represent Compton effect. Now, with this explanation, let me define what is meant by Compton effect. The phenomenon of decrease in energy or increase in wavelength of X-rays after scattering from the surface of an object is called as Compton effect. Suppose if we consider that the amount of wavelength which has been incidented on X-rays is symbolically represented as lambda, so then lambda dash is the wavelength of the scattered X-rays. So then the change in wavelength, that is delta lambda, which means the change in wavelength will be equal to lambda dash minus lambda, which is equals to h divided by mc into 1 minus cos theta. So this is a mathematical expression of Compton effect. So what I said, like Compton found that wavelength is not dependent on the intensity of incident radiation, but it is dependent on the angle of scattering and on the wavelength of the incident beam. So this can be represented, or it is given in the mathematical form as delta lambda is equals to lambda dash minus lambda, which is equals to h divided by mc into 1 minus cos theta. So here delta lambda is nothing but change in wavelength or difference in wavelength. Okay, and in this expression, lambda is the wavelength of the incident X-rays and lambda dash is the wavelength of the scattered X-rays. So delta lambda is the increase in wavelength and it is called Compton shift. So delta lambda is independent of the nature of the substance and lambda, and it is dependent only on theta, that means only on the angle between the incident and scattered rays. The wavelength shift is independent of the nature of the substance and wavelength of the incident X-rays, and it depends only on the scattering angle. Scattering angle is nothing but theta. Depending on the scattering angle theta, we have the following cases. That is, case 1, if theta is equals to 0 degree, then cos theta is equals to 1. If cos theta is equals to 1, then delta lambda will be equals to 0. Go back and see this equation. So suppose here if cos theta is 0, then delta lambda will be equal to 0. Okay. Next, in case 2, if theta is equals to 90 degree, then cos theta is equals to 0. In case 1, if theta is equals to 0 degree, then cos theta is equals to 1. Then the whole term will become 0. Why whole term will become 0? Here 1 minus 1 will be equal to 0, and 0 multiplied by any object, so it results in 0. So that is why delta lambda will be equals to 0 in case 1. Whereas in case 2, if theta is equals to 90 degree, so here theta means what? Theta is the scattering angle. So when an incident ray falls on carbon, to what extent so the electron is going to get scattered. So this is the scattered photon, and this is called as recoil electron. And what is the angle measured here? Okay, so I am talking about this angle. So here we are discussing the different cases, what are the possibilities. So first case, suppose theta is equals to 0, then delta lambda is equals to 0. And the second case, if the theta is equals to 90 degree, then cos theta is equals to 0. Okay, so suppose if it is 90 degree, then the scattered radiation is perpendicular to the incident radiation. Okay, so this is the observation which we are going to make. So in this case, cos theta is equals to 0, so that what happens is delta lambda is equals to h divided by mc. So 1 minus cos theta, so that is not considered here. H minus mc means what is the value? All constants are here. Okay, h is Planck's constant. So m is mass of the electron and c is the velocity of the light. All are constants. Substitute the value. H is equals to Planck's constant, that is 6.626 into 10 raised to minus 34 joules per Siemens. And what is the mass of the electron? Mass of the electron is 9.109 into 10 raised to minus 31 kg. And what is the velocity of the light? Velocity of the light is 3 into 10 raised to 8 meters per Siemens, right? Substitute the values and what we are going to get is 0.0242 Armstrong, or in terms of pm we can write it as 2.42 pm picometer. Okay, so picometer, pm is nothing but picometers. So this is the value of or the difference in wavelength. So this is delta lambda we are calculating here. So the difference in wavelength will be 2.42 picometers. So suppose the third case explains that suppose if theta is equals to 180 degree, so then cos theta will be equals to minus 1. So minus 1 means what? So 1 minus in the bracket again minus 1. So that gives the value of 2. So delta lambda or the change in wavelength is equals to 2 into h divided by mc. So h divided by mc value we have already calculated here, 0.042 Armstrong, 2 into 0.0242, which is equals to 0.048 Armstrong. So suppose if theta is equals to 180 degree centigrade, then the change in wavelength, that is delta lambda, will be equal to 0.048 Armstrong. Okay, so these are the three different cases which we observe based on studying this Compton effect. So what are the observations or outcome of this Compton effect? So Compton effect provides a good illustration of the uncertainty principle. Suppose X-rays are used to determine the position and momentum of an electron. As a result, a mutual interaction of X-rays and the electron, so the wavelength of X-rays increases, that is, the energy of X-rays decreases. So as the wavelength increases, the wavelength of X-rays increases, the energy of X-ray is going to get decreased. So this energy which has been transferred to the electron, whose energy will therefore change, and so the momentum will also change. So this is what is called as uncertainty principle. So the energy which has been transferred to the electron, whose energy will therefore change, and so the momentum will also change. So this you will understand in a better way when we discuss about Heisenberg's uncertainty principle. So what does that Heisenberg's uncertainty principle says that? So it states that it is not possible to determine exactly both the position and momentum of small moving particles. So that is what is called as uncertainty principle. In the same way, here in Compton effect, so the energy which changes, and it will also result in the change in the momentum. Consequently, the momentum of the electron cannot be determined with certainty. Not only the momentum, even if you want to determine the energy, so by considering both energy and the momentum, we cannot predict it in a certainty. That means the exact energy could not be predicted or found out or determined. So diffraction and interference of radiation provide evidences for the wave nature of radiations, while the photoelectric effect and Compton scattering provide evidence for the particle nature of the radiation. So this is another important observation which has been made by studying this Compton effect. That is, so the two concepts which are very important with respect to the physical chemistry, that is diffraction and interference of a radiation. So by studying this Compton effect, it has provided evidence for the wave nature of the radiations, while the photoelectric effect and the Compton scattering, they both provide evidence for the particle nature of the radiation. So this plays an platform or basis for our further studies, so where in my next class we will understand about de Broglie's hypothesis. What is meant by de Broglie's hypothesis? So it is nothing but it is just to prove that so the dual nature of matter and radiation. So it just explains that so a matter or a radiation, it has dual nature. So it also has got wave property, wave nature, and at the same time it is observed that so it is also having the nature of a light, which is considered as a particle. So it has got both wave nature and also a particle character. So that is what is very interesting with respect to de Broglie's hypothesis. So now let us not distract too much. Let us come back to this Compton effect itself and let us solve one simple problem, so that how the application of this Compton effect is used in finding out the wavelength of a scattered beam. So here the problem says that a monochromatic X-ray beam of wavelength 0.558 nanometer is scattered through an angle of 46 degree. So here he has given lambda, so that is the incident radiation's wavelength has been given lambda, and also so the angle of scattering, angle of scattering is nothing but theta is given, so theta is equals to 46 degree. What is the wavelength of the scattered beam? So he is asking to calculate us what will be the wavelength of a scattered beam. The incident wavelength is there. The incident wavelength of monochromatic X-ray beam has been given, that is 0.558 nanometer. So let us consider the same equation or mathematical expression which we deduced for Compton effect. So delta lambda or change in lambda, which is equals to lambda dash minus lambda, which will be equal to h divided by mc into 1 minus cos theta. So this is the mathematical expression of Compton effect. So here what is needed, substitute the values. So as I said, he has given the wavelength of incident radiation, that is 0.558 nanometer, right? And he has also given theta, which is equals to 46 degree. Okay, so now subtract this lambda dash minus lambda, which will be equals to 0.0242 into 1 minus cos 46 degree. Okay, and now I have taken this lambda dash because I want to find out the wavelength of the scattered beam. So wavelength of the scattered beam is represented as lambda dash. So lambda dash has been taken into left hand side. So this is equals to 0.558 plus 0.0242. So this is 0.0242 is nothing but the value of h divided by mc. Okay, so into 1 minus so cos 46 degrees 0.6947. So if you have scientific calculator, you can just check it out. Okay, and if the problem is asked in the examination, then you have to use a scientific calculator to find out the value of cos 46 degree or whatever the angle which is which they have given, 50 degree or 56 or 62, whatever. So here 46 degree, cos 46 degree is equals to 0.6947. So substitute that value, we are going to get 0.5587 nanometer. So therefore the wavelength of scattered beam is 0.5587 nanometer. Okay, so in this way Compton effect is used to find out or to calculate the wavelength of scattered beam. So next what we have to understand is it is about comparative study of photoelectric effect and Compton effect. So here I have made 4 points to study the comparison between photoelectric effect and Compton effect. So what are those 4 points? We'll see one by one. So the first is both photoelectric effect and Compton effect result due to the action of a photon with an electron. So here both photoelectric effect, Compton effect involves or includes the action of a photon with an electron. A photon is nothing but a radiation, a monochromatic X-ray, okay, so or a light, so which is going to fall on a matter or on a metal thin foil, where we saw in photoelectric effect when a radiation falls upon a thin metal plate or foil, so electrons are ejected. So in the same way in the Compton effect also, so here when a monochromatic X-ray hits upon a carbon or any other metal, so there we are going to observe the scattering. So that is why, so in both photoelectric effect and Compton effect, so the result is due to the action of photon with an electron. And the next is the laws of conservation of energy and momentum are valid in both the effects. So what is meant by laws of conservation of energy? A laws of conservation of energy is nothing but Newton's third law, right? So energy neither be created nor be destroyed, but it can be transferred from one form to the another form. So that is what is called as the law of conservation of energy. So here in both photoelectric effect and Compton effect, laws of conservation of energy and momentum are valid, and it has got equal effect in both, that is photoelectric effect and Compton effect. And the third is in photoelectric effect, the energy of the incident photon is completely transferred to the free electron in metal, but in Compton effect only a fraction of energy of the incident photon is transferred to the loosely bound electron. So this is the comparison between photoelectric effect and Compton effect. So what happens in photoelectric effect, as we have understood in my previous class, here in photoelectric effect the energy of the incident photon is completely transferred to the free electron in the metal, whereas in Compton effect only a fraction of energy of the incident photon is transferred to the loosely bound electron. And the last observation or comparative study of photoelectric effect and Compton effect is that, so if the energy of the incident photon is greater than the work function of the metal, then the electron is ejected, okay. So whereas in Compton effect the electron is recoiled after the scattering of the photon. So here in case of photoelectric effect, the energy of the incident photon should be greater than the work function. So that is nothing but, so we understood a concept which was known as threshold frequency or threshold energy. So that means so the energy of the incident photon should be greater than the work function of the metal, then only electron is ejected from it, leaving a positive charge. But in case of Compton effect, we observe that the electron is recoiled after the scattering of the photon. So these are the 4 main comparative studies so which we can make between photoelectric effect and Compton effect. So along with this, so we can add up some more differences between Compton effect and photoelectric effect. So they are like, so Compton effect, it is explained by Arthur Compton, okay, and photoelectric effect is explained by Albert Einstein. And next is in Compton effect, the energy associated with the free electrons is in mid energy, whereas in photoelectric effect the energy associated with the electrons is low energy. And in Compton effect, the wavelength of the scattered photon is higher than that of the incident photon. Whereas if we come to the photoelectric effect, the wavelength is not observed as the photon disappears after interacting with the electrons. And in the same way, so this is the effect which is caused by the inelastic scattering of high energy photons that are bound to the free electrons, whereas photoelectric effect is caused by the weakly bound electrons that are ejected from the surface of the material when electromagnetic radiation interacts with the electrons. Okay, so in this way, so lot of differences and also the comparative studies could be made between photoelectric effect and Compton effect. I hope you understood the concept of Compton effect, what is Compton effect and who invented this, and how we are going to represent Compton effect in terms of schematic representation or diagram. And also I have defined what is a Compton effect and how we are going to express this Compton effect in terms of mathematical expressions, and what are the different cases we are going to study depending upon the scattering angle, which is called as theta. Okay, and next we also understood what are the keen observations or the outcomes of Compton effect. Okay, and next we learnt how to solve a problem or to find out or to calculate the wavelength of the scattered beam by solving one simple problem. And at the last part of this session, so we understood the comparative study of photoelectric effect and Compton effect. Okay, so I am going to stop it here, and in my next class so let us understand about de Broglie's hypothesis. So about de Broglie's hypothesis, I already gave a slight introduction, that is de Broglie's hypothesis is nothing but it is the way to prove that the light or the nature of matter and radiation, it has got a dual nature. So it is not having only the wave nature, or it is not having only the particle character, it has got dual nature. So how the de Broglie explains this with the help of all these concepts which we have already studied, like quantum theory, which has been given by Planck. Okay, Planck's quantum theory, we are going to use that, and along with that we will understand so how de Broglie is going to prove that the wave or energy has got dual nature, which is represented as a dual nature of matter and radiation. Okay, so let us meet in next session. Thank you, dear students.